for computational media intelligence. My name is Sri Narayanan. It gives me great delight to introduce today's speaker, Professor Christina Lerman. Christina is a principal scientist at our Information Sciences Institute at the University of Southern California, where she's also a research professor in computer science. Trained as a physicist, Christina brings broad computational thinking to many problems, especially that are connected with today's way people use information, process information, and how information is used to sort of modify people's behavior at various scales. And personally, I've been honored to have been her colleague and collaborator, and continue to be so. And one of the areas where Christina has been sort of actually pioneering a lot of efforts is in considering from a bias and fairness perspective, how not only do we create these methodological approaches and what their impact are, how can we actually mitigate some of these questions in variety of data forms, whether it comes from social media or even comes from, sensors on people and so on. So we are super delighted to have Christina join us today. This is a seminar, the fourth seminar in the series this semester, hosted jointly by the Center for Computational Media Intelligence at USC, alongside colleagues at Google Research involved in media understanding and social exploration. Thank you so much, Christina, for joining us today. And if you have questions, you can put it in chat or wait until the end of the seminar for discussion. But any clarification questions, please feel free to sort of turn on your video and ask the question, or you can wait until the end.
Yeah.
Christina,
thank you.
The floor is yours.
Thanks, Sri, very much. Thank you for the gracious introduction. I do welcome questions, even if stop me during the talk, gives me a chance to pause and slow down. And so let's go start. And if you don't mind, I'm going to share my stop my video to conserve bandwidth. All right. So let's just get situated here. Plus, I lost my slide presentation. Okay. So actually, I'd like to first advertise that I teach a class at USC on fairness in AI, and the class covers biases in different forms of data, including social data that I'm going to be talking about mostly now, focusing this talk. We also cover language and networks, which is another one of my specialties, and how these biases in these types of different data can introduce unfairness, can promote discrimination. And in this talk today, I'll give you some flavor what the course covers and how the relationship between biases in data and fairness in AI. Okay, so in social science, very often, when you deal with social data, you're given some data sets, some measurements. Here, for example, we're having measurements of life expectancy in different countries and comparing it with an obesity rate. And then you're asked to look for a relationship within these data, which will lead some sort of insight into human behavior. So given this data set, what we've seen, scatter plot, and the scatter plot usually looks like a cloud of data points. This is what all social data looks like, a cloud of points. The question is, how is life expectancy, average life expectancy at birth, related to obesity rate within the population? And if you look overall over this many different countries, it looks like the relationship is positive, meaning the more obese, the higher the obesity rate within the population in the country, the longer the life expectancy. And I apologize ahead of time to be, bring up this, and I need to find another example that might not be maybe uncomfortable for people, but this illustrates kind of a very common problem that exists in data. And so on the one hand, this relationship is surprising, because what we've been taught that obesity rate is not conducive to higher life expectancy. So what's going on? Is this actually really a relationship? What's going on in that? So this is, as I will show you later on, this type of misleading behaviors are very common in social data analysis, because population of countries as a whole is composed of very different countries. the population of countries is heterogeneous. Some countries, for example, are affluent countries, and some countries are poor countries. And within each of these, the relationship actually might be very different. But when you take population countries overall, you will get a misleading result, positive correlation, because of the hidden interrelationships and hidden structure within the data. For example, if you look just at the affluent countries that are composed of nations with high GDP, you are going to see that actually there's a negative relationship between life expectancy and obesity rate. Whereas in countries that are developing countries, for example, the relationship might still be positive. So this is what my talk will be about, how basically as a cautionary tale about how these hidden relationships in data that bias the data, how these hidden relationships in heterogeneous data, they pose threats to the validity of the models, statistical models you might want to learn from the data. How these models then might pose threats to predictions. They lead to non-generalizable, non-reproducible results. They have poor performance on held out data unless you take into account these hidden relationships, these hidden confounders in the data. These confounders also pose threat to explanations. So here we have, for example, ecological fallacy to learn to make predictions for an individual based on some group level dynamics, which might often be wrong. These also these hidden confounders may lead you to make misleading or even wrong inferences about behaviors of individuals, which will impact the kind of interventions you might want to design. And finally, I'll show you how models learn on biased data might also entrench or amplify discrimination. The models might be unfair and lead to promulgate discrimination and prejudice through the predictions they're making that they learn on biased data. So this is kind of overview of the talk. Here's more specific outline for the talk. First, I will talk about a variety of biases that arise in heterogeneous data. And I'll talk about some of the methods that we are developing to deal with these biases to analyze heterogeneous data. And here I'll focus only on Simpson's paradox. And then I'll talk about algorithmic fairness and how we might even not only how models might be unfair, make unfair predictions, but how we might actually debias the data to create more fair models. All right, so the first talk. So there's a great variety of biases. All data is heterogeneous. It's composed of differently behaving individuals or subgroups. And depending on how this data is aggregated, how the data is collected, you might actually select the different slices of the population through the data, and the slices, selected data that you get might actually tell you a different story about individuals. That's what's going on in reality. So I will cover some of these biases. Probably in the interest of time, I won't have time to go over all of them, but I'll give you a flavor for what they are. So I'm going to start with my favorite one that actually started me on this journey of understanding biases in data. This is Simpson's paradox, which has actually been known for over 70 years, but it crops up everywhere in every single data set that you look like. So Simpson's paradox is illustrated in this example, where it actually, you see that the trend, one type of trend might exist within individual groups, but the trend will disappear or even reverse when you aggregate the groups together. So a population level trend might look just like in our obesity example. The population level trend looks positive, but within each group, the trend can be actually negative. And this is actually even can be related to biases in fairness in data. This Simpson's paradox. Here's a famous example some of you might have heard about bias in data, where this was actually a Supreme Court case, I believe, where UC Berkeley was accused of discrimination against women, because when you look at the graduate applications data, you see that higher fraction of men were admitted for graduate studies to UC Berkeley than women. 43% of male applicants and 35% of female applicants were admitted to graduate studies. So Therefore, the conclusion was that the university was discriminating against women. But a more careful analysis of data, when you actually disaggregate admission statistics over different departments, you actually get a completely different story. So in this, that's 1, 2, 3 to 6 are different departments, and you can see that the bars show the fraction of male and female applicants admitted in each department. Okay, so overall, you see that the admission rates are really different. Some departments are really difficult to get into. For example, they admit fewer than 10% of their applicants. And some departments are very easy to get to. They admit more than half of their applicants. Moreover, within each department, actually, women have parity, or even they're doing it better. Higher fraction of women are admitted within each department, or almost as many. So how does this bias arise? The fact that more men are admitted, whereas within each department, higher fraction of women look like at least as many or higher fraction of women are admitted. Well, both of these are actually true statements about the data. And the problem is that more women tend to apply to departments like department number 6 and 5. More women apply here to departments that are harder for applicants of either gender to get into. So these are very hard. They're departments that have very few slots for PhD studies. So they admit very small number fraction of candidates. They're probably departments like English and history. And relatively few women apply to these departments, 1 and 2, which admit a large fraction of their applicants. So they have many slides. So these are probably STEM and engineering departments. So the discrimination against women still exists, but doesn't exist within admission statistics. It exists within the entire pipeline, education pipeline, which channels women into studying things like history and English that have fewer slots for advanced scholarship than other departments. Okay, but this is like one of my favorite examples of Simpson paradox, and shows how it really might relate to fairness as well. No questions? Next one. So another type of bias that affects data and conclusions drawn from data is the survivor bias. Here's another famous example of survivor bias, where during World War II, fighter planes were coming back from battle. You know, they had a distinctive pattern of damage. So an engineer was tasked, you know, to which parts of the plane should you reinforce to keep the more planes coming back from battles. Even if it was damage in that area, it wouldn't be coming back. So it would still come back. So offhand, you know, your gut reaction is to reinforce parts of the plane where a lot of damage is seen, right? The like tips of the wings, or maybe the main part of fuselage here. You should reinforce those areas. But that's actually wrong. The things that you should be reinforcing is where you don't see much damage in the planes that came back. Why? Because the planes that actually had damage in those areas, in those parts, they're the ones who did not come back. They're the ones that crashed and died. Whereas these are exactly the parts where you're not seeing the bad damage. There's exactly the parts where you should reinforce. You know, these parts that you can see the damage. Well, the damage occurred, but it wasn't fatal, and it didn't prevent the plane from reaching the home base. So those are less critical to reinforce these areas. So here's basically survivor bias, the fact it says that the parts of the data that we do observe might not be a representative set of the entire population due to survivor bias. And it crops up everywhere in data analysis. Here's an example from one of the papers I read. It's an older paper, but I still think it has very illustrative examples. It talks about recidivism rate, for example. So imagine offenders. They've served their time in jail and convicts, and they're released from prison. And what you want to know is, you know, how many of them commit another crime, reoffend in the future, and return back to prison. So if you plot the rate at which they go back to prison over time, you will get a decreasing trend. Many of us have seen such a decreasing trend and are familiar with the conclusion. Generally says that, oh, okay, what's going on here? Well, as convicts that are released from jail, as they get older, you know, with time, as time passes and they get older, they become more pacifists. They become less likely to offend. They become more law-abiding members of society, so they're less likely to commit a crime, and they're less likely to return to jail with time. But this could be, nothing could be further from the truth. What's going on underneath is actually there are two populations. There are some people that, let's call them the reformed. Once they're released from prison, they're not highly likely to commit another crime. They will commit it at some very low rate. They want to be good citizens. They want to be reintegrated into society. They will not commit another crime. And there's another population of convicts who are released from prison. They're the incorrigibles. They will, no matter how long time has passed, they're highly likely to commit another crime and be rearrested. So what happens over time? Well, over time, these incorrigibles, they commit another crime, they're in prison, there's fewer and fewer of them in the population at large. So characteristics of the population change as a function of time. There's fewer and fewer of this group, the incorrigibles, and because of that, the overall rate looks like it's declining, whereas the rate within subpopulations is constant with time. People do not change over time, but the proportion of people of each type changes over time. So this is an example of this type of survivor bias that leads to kind of a Simpson's paradox, where the trend for the population overall may be different from the trend within underlying subgroups. And we see it everywhere. I'm just showing one example, but I've seen it in several different social and online platforms that we studied. Here I'm showing an example on Stack Overflow, which is a question answering site. So you ask programming questions and other people answer them. So we were just simply curious if people actually learn from experience, and as they write their answers, as they answer questions, their answers get better and better with time. So generally, somebody, Stack Overflow, somebody asks a question, community answers the question. So somebody might, Stack Overflow user might sit down and start answering first, second, third, answer several questions. And then one of those answers will be, that the user writes, one of those answers will be accepted by the asker as the best answer to the question. So accepting whether or not an answer is accepted as a good answer, it somehow measures its quality. So we were simply measuring how likely an answer to be accepted if it's a first answer written during the session, second, fifth, 10th, 15th, or so forth. And if you look at the population as a whole, it looks like every subsequent answer that the user writes is more likely to be accepted by the asker as a good answer to the question. So that it looks like the quality of answers is going up. So it looks like people are learning how to answer questions and getting better at it.
Sheena,
but yeah,
there seems to be a question. Yorgos?
Yeah, just a quick question for the previous slide. How were the two groups, Me1 and Me2, separated?
In this paper, they actually did not explain how the was separated, but they were referencing criminological studies. So I think there is some sort of survey or some sort of way to separate those two types of populations, two types of groups. So, and this is actually, I mean, I got the feeling this is all hand drawn, but it's based on actual data. Just because the paper from 1985, because there were good layout, page layout algorithms, that's why the data looks like they're just cartoon examples, but they're actually based, all the examples in this paper are based on actual examples and actual data. So unfortunately, I cannot answer this question, but I think he relies on criminological data. But it's much easier to answer this question, how those groups are disaggregated in my own work. I can tell you that. So, okay. So in Stack Overflow, it looks like the quality of answers is increasing over time. But you have to think that, answers is highly heterogeneous. There's some newbies, or some infrequent users that only answer 1 or 2 questions. And there are others who are, gung-ho users who answer many, many questions, power users, so to speak. So instead of analyzing population as a whole, we actually disaggregate based on the length of the session. How many answers does a user write in a session? So we only look at the acceptance probability of answers, all answers written during the session where only 5 answers are written. Or acceptance probability of answers written in the session where only 2 answers are written, and so forth. So in all of these, once you disaggregate the data across sessions of any length, we actually see that the first answer is more likely to be accepted than the second answer. And second answer is more likely to be accepted than the third answer, and third answer is more likely to be accepted than the fourth answer. So this is a general trend that probability of acceptance actually decreases over time. So which indicates that people are writing answers that are not as good, that are worse than previous ones. So why is this happening? Actually, there is a theory that was proposed, pioneered by Roy Baumeister, talking about cognitive depletion or ego depletion, as they called it. So his idea that they have, Roy Baumeister has done it and validated it in lab experiments where people are asked to do some tasks that require effort and cognitive control. So his idea is that any kind of mentally effortful task, like solving difficult math questions or holding your hand in icy water for a long period of time. So when you're asked to do these effortful tasks, it actually depletes you, leaves you with less energy to make good decisions or to exert mental effort or practice willpower later on. So this type of, like I said, we observe it over many different platforms, including Reddit and Facebook and Twitter. This indicates that kind of people spend effort to write questions, and that leaves them with less mental energy to do a good job or less time to answer later questions well. So this is basically cognitive depletion leads to worse answers over time. Okay. And this seems like the general trend. Another type of bias I'd like to talk about is actually aggregation bias. And this is something that's been known by geospatial analysis people, people doing geospatial analysis for a long time. So this is a statistical bias that affects results when data is aggregated. So whenever you compute statistical estimates, for example, you're computing a total, a rate, a density, it really matters what the scale and the shape of the unit of data that you're aggregating. And we found there's actually there's a systematic bias when you average growth rates that we actually discovered when we were analyzing COVID growth rates in the United States. And this seems to be also a more general result. So we call it aggregation bias. So, well, we're still living in the pandemic, but looking at the first half of the pandemic, first year and a half of the pandemic, remember there were like all this, like this is number of cases, number of infections in the United States overall, and you see there were 3 surges. So we are actually measuring growth rates, and then we'll show how the spatial scale at which you are measuring the growth rates actually affects the growth rates that are measured. So we're measuring the early growth of each surge, where the growth rate can be approximated by an exponential growth rate. So we can fit a negative binomial regression model to estimate the growth rate within the surge. And then we can compare those growth rates of COVID infections, cases or deaths, actually, for different spatial units, for counties, US states, or the nation as a whole. And what we find is, as you go through this exercise and you estimate the growth rates within counties, and then you aggregate the county data together to get state, and then estimate growth rate for the state, you actually get systematically different results. So the growth rates at the state level are systematically higher than the growth rates at the counties, within counties that compose them. This is true for infections, growth rates. This is also for death rates. Looks like death rates are increasing faster at the state level than at the level of the counties, and faster in the nation as a whole than within the states or counties. So So spatial aggregation looks like it amplifies the growth rates. And why is this happening? It's because, I'll show you later, it's because of the development of hotspots. The neighborhoods or the country is the growth rates are highly heterogeneous all over the country. So there's few hotspots, and these hotspots dominate statistics and they skew the aggregate growth rates. So here, for example, I'm illustrating with New York State. So each line is for a different county within New York State. In New York City is the most, so the black line is for the state as a whole. But the state as a whole line is basically an aggregation over different counties within the state. New York City have combined 3 counties actually together. This forms New York City. It actually has the highest, it contributed the most to the aggregate. So the virus grows exponentially within each county, but at a different rate. So it grows faster within the denser, more populated counties, and also arrives in each county at a different time. Some started growing earlier than others, and together, it's the ones that arrived earlier develops into this hotspot. Hotspot basically skews the aggregate count for the state as a whole. And this also holds true for if you break down. If you look actually within New York City, look at different zip codes, or within LA County, you look at different neighborhoods, you'll see the same story hold true. That overall, the virus looks like it's spreading faster in LA County as a whole than within individual neighborhoods, just because there's a few neighborhoods that were spreading the highest. And I was showing you, illustrating with growth rates during the first surge, but the same as applies actually to later surges as well, to the second and third surge, and you can actually see the estimates. There are actually 2 important points, actually. First of all, aggregation bias still exists in later surges as well, because the estimates of growth rates for states looks like higher than for counties, and for the nation as a whole is higher. Another thing, and actually you can see it here, you can see, for example, New York State, this is showing counties, growth rate within different counties, and you can see New York City is the heavy one here, but then contributes to the higher, darker color. Darker color means it's higher growth rate within the state as a whole. But you can see within each subsequent surge, the growth rates actually decrease. The COVID is growing more slowly within each subsequent surge, but you remember that surges actually reached higher and higher is because they're actually starting from a different baseline in each time. So even though it's actually the growth rate is less than previous surges, because it's starting at a higher base rate, it's actually like cases become much bigger than previously. Okay, any questions about aggregation bias? There's actually other interesting in this paper that I'm citing here. There's also interesting points to be made about kind of heterogeneous growth rates and how you get scale-free or parallel distribution of impact across the world, and what it shows about the model of epidemics, how they're growing. But you can please, you can Google the paper and see it. Okay, so my next point I'd like to, so those were basically a whirlwind tour through some of the biases that affect the data. But the question is, how do you know when your data is biased? There's what are the hidden confounders that might be polluting or influencing the results? And I have several papers that are trying different approaches to discover this. I'm going to just highlight one that I think is most kind of accessible and easy to explain. And this is the paper that attempts to automatically discover when the Simpson's paradox is actually affecting your results. So this method simply takes all the data, all the features, covariates you've observed, and it systematically disaggregates the data based on these observed features into more homogeneous subgroups, and then looks for functional differences between the subgroups and the pooled data. So here's two papers that describe this approach, and we actually have code is on GitHub, which actually works with binary predictions, binary outcome variables that you can try it yourself. So what does it do? So just like I was talking about Stack Overflow, you have some outcome, which is acceptance probability. You're given some data which has outcome, which is probability the answer is accepted, it's a good answer. And then you have many predictor variables. One of them could be position of the answer within the session. Is it the first, second, third answer that's written in the session? Could be other covariates, could be users' answers reputation, how long they've been around, how many words the answer has, how many URLs are included in it. Could be, you could think of a variety of different features. So, but you're trying to explain the relationship between the outcome, which is acceptance probability, and answer position. So the second step in this approach is it fixes this outcome variable and the covariate, but then it bins the data according to another feature. So for example, within answer position, and maybe user's reputation would be the third, third feature. And the algorithm will bin the data according to user reputation. A lot of the magic is happening here because finding appropriate binning for the data is not a trivial task. So it bins the data according to user reputation, for example, and then it looks for trends within each bin or within each group, because the basic idea is that people within this group, people who have similar reputation with each other, they might be behaving in a similar way. So this should be the proper level of analysis. And then if the algorithm finds that within many of the bins or within many of the groups, the trends have changed with respect to pool data, it will report it as one of the paradoxes. And as I said, we've applied this method to many different platforms. And this one I discussed before with the trend reverses, but we have actually seen it also in other groups as well. So within Reddit, for example, also if you disaggregate on session length, it becomes this important variable that you need to disaggregate the data. And when actually that is categorical, it's easy to disaggregate. You just create a different group for each category. But when it's continuous variable, you can also disaggregate data based on continuous variable, but it's more tricky. So in Reddit, for example, the quality of the comment depends on whether it's first or second or third. It should goes down. So you can quality of the comment, you can measure it by the length of it. So the longer comments are written first, and then comments get shorter. The score upwards it received also, the early comments get more upwards than later comments. Number of responses, the same thing applies. Early comments get more responses than comments written later in the session. And readability also changes, how easy, early comments are easier to read than later comments. It also works in Facebook. If you look how much time people are spending browsing through their feed, it looks like people actually kind of slowing down, they're spending more and more time later in the session, but it's actually, again, it's kind of survivor bias or Simpson's paradox, where you disaggregate into sessions of different length. Actually, people spend more time reading each post earlier in the session, and later in the session, they're actually skimming them faster and faster. And the longer the session they have, same rule applies. They spend more time early in the session, and they spend less time skimming each post later in the session. Okay, so this is one approach. We have a couple of other approaches that also look to disaggregate data. In addition to observed features, they look to disaggregate data on unobserved features. But finally, in the last part of the talk, I'd like to show the relationship with algorithmic fairness and some of the issues that arise from biased data. Okay. So first, though, we need to start with what does it mean to be fair? And there's a number of definitions. This actually makes the problem really interesting, because you can define fairness in very different ways. But there's some intuitive property of fairness that we all adhere to, that says that your private attributes, such as race, gender, age, personality, maybe even, your private attributes should not affect how you're treated by the algorithm, especially in cases when these properties are not relevant to the task at hand, the decision being made. Okay, so this is kind of like intuitive that we can probably all agree on this, but operationalizing this definition is really hard. So there are actually dozens of measures of fairness that exist out there. And many of them are even make the problem even more challenging, that many of these measures are incompatible with each other. And as I'll show you, they can be simultaneously satisfied in just a few special cases. And as I said, this makes this problem really interesting as well. So the field of AI fairness really, it got started more than 10 years ago, but it really became big in 2016 when ProPublica came out with this analysis of Compass. Compass is a tool that's used by judges to evaluate the recidivism risk of individual defendants. And so, for example, it will take into account the defendant. It's supposed to help judges make quicker and less biased decisions. So Compass will, as each defendant comes before a judge, Compass will take defendant's history, like prior arrests, what they were arrested for, some, the time that they were, when were they first arrested by police, the demographics, and would produce a risk score, which is supposed to convey how likely they're to offend in the future. And the judges use this risk score to basically then decide whether or not this person should remain in jail or maybe should be released, and what kind of conditions they should be released under. And what ProPublica found is actually that these predictions were racially biased. Okay, but before we get to these racially biased predictions, actually, we should first look at, take into account the fairness scores of what the algorithm was doing. And because the Compass, the makers of the tool, North Point was the maker of this Compass tool, they actually did want to make it an unbiased algorithm. But what they were looking for, actually, they were looking for calibration of risk goals. So one of the fairness goals that algorithm should be well calibrated. So the predictions should be well calibrated, which means that whatever the algorithm says, that within, whoever the group that individuals assign some risk score, that group should be committing offenses at that rate, no matter which group it is. So, for example, if the algorithm supposes it sets a group of individuals, it gives them score 1. This means that 10% of individuals from this bin will commit another crime. 10% of individuals, regardless of whether they're black or white, for example, or men or women, they should have the same rate of committing a crime. Okay? If the algorithm assigns a risk score of 6 to some individuals, and all individuals within this group who are assigned a risk score of 6, 60% of them should commit a crime, another crime in the future. 60% of whites and 60% of blacks should commit another crime in the future. So this is what, there's some benefits for, this is one measure of an algorithm being fair. If it's the prediction it's making actually hold true for within each group. So ProPublica was able to evaluate this kind of fairness and other definitions of fairness as well in the algorithm. What they actually had access to was that about 7,000 people who were arrested in Broward County, Florida. So it had the demographic characteristics for those defendants. And importantly, because they were doing the study in 2016, which was like 2 years later, they could see whether within the span of 2 years, whether those people were arrested again. So they knew what the ground truth is. Did the person reoffend or not? We can argue whether getting arrested again is actually a good ground truth label, but nevertheless, they took that as a ground truth label. Was the whether the person actually did they commit the crime, basically were they arrested again within the 2 years after their score. And then they can actually see what prediction did the compass make, what risk score did the compass assign to them in 2013 or 2014. Okay, so it's clear? So you can actually look at this in a kind of traditional machine learning way to evaluate traditional machine learning way. Here's the prediction given by the risk score. So the prediction could be low risk score, saying the defendant will not commit crime, or it's a high risk score, saying the algorithm believes the defendant will commit a crime in the next 2 years. And then you can see what actually happened. Did the person commit the crime or did not commit the crime? So you have true positives and true negatives, which is determine the accuracy, how well the algorithm is doing. But of course, any algorithm is not going to be perfect. It will make mistakes. So where are these mistakes located? So there's two types of mistakes. There's the false positives and the false negatives. And what actually ProPublica did was showing that these mistakes were not borne equally by the two groups, by the two racial groups. So I hope this type of format is actually, if you're a machine learning person, this is all familiar with you, you know how to evaluate. So first of all, actually, first, North Point's compass. Compass is actually, North Point said we actually took fairness really seriously. We took great pains to calibrate the predictions so that the actual probability of recidivism was related to the risk score. So, well, I should say the other way, that the risk score was related to probability of offending. And indeed, actually, if you plot what's the fraction of people within each risk score bin were arrested again, you'll see it's actually, first of all, it's proportional to the risk score, and secondly, it's more or less the same for the two racial groups. Blacks and whites have the same probability conditioned on predictions. So it seems that compass is fair, but it's not actually. Because there's not a measure of fairness, which looks at the false positives and the false negatives. So balance, for example, if you consider the negative class, people who did not commit negative class, then you can actually look at the false positive rates and how racial disparities within the false positive rates. So balance for negative means saying that average scores for the negative members in one group, for example, people who did not offend, should be the same as the average score of negative members in the other group. People should, so because risk score should not be systematically more inaccurate for one group than another. What is happening in compass? This plot is showing, what risk scores were assigned to people who never committed another crime. So these were negative instances for the purposes of classification algorithms. So these people never offended again, but let's look at what their risk scores are. So there should be more people here given low risk scores because they didn't offend, so that's correct. But then if you look at this other, at the high end of the scale, you see many more blacks were assigned high risk scores than whites. More than twice as many blacks were assigned high risk scores than whites. And the same thing is true also for positive examples. So defendants who did commit another crime, so they should be given high risk scores, correct? But defendants who did commit another crime, if you look at algorithm mistakenly gave a low risk score to many more whites than blacks. So the algorithm, in other words, algorithms making mistakes at a different rate for blacks and for whites. So what's going on? So on the one hand, we have well-calibrated algorithm. On the other hand, it's not balanced. So this is because these calibration and balance represent two different faces or facets of fairness, and there are actually many other facets as well. This is basically this calibration is saying conditioned on predictions, your outcome should not depend on race. And the balance condition is saying, well, conditioned on outcomes, whether the defendant did commit another crime or not, predictions should not be dependent on race. And it wasn't until, and it happens that these two definitions of fairness, they can only be simultaneously satisfied in special cases, only in two special cases. One special case is perfect prediction, when the perfect oracle can exactly predict for each person whether they will commit another crime or not. So then the algorithm will be both calibrated and biased. And another condition is equal base rates, when there's no difference between the two groups. Well, there is no difference between the two groups, blacks and whites, at how often they offend, then there's no reason to discriminate at all. There's no discrimination. The two groups are the same. There's no. So, but except for these two cases, in all other cases, you cannot actually satisfy both of these conditions together. So this is one challenge of fairness, that these different fairness conditions are not compatible with each other. And there's inherent trade-offs between them. Another challenge is that, I'm sorry, this is hiding over this, but when you make a predictions more fair, when you reduce the burden of mistakes, you necessarily reduce the accuracy of predictions. So the overall accuracy becomes less when you enforce the constraints of fairness. So that's another challenge of fairness. But actually, so those are the challenges, but you still have a lot of room to improve. But you can make decisions more accurate, but maintaining fairness, or you can improve fairness by maintaining accuracy. So this is a very active research topic right now, and there is a variety of approaches right now. The most common ones, the most popular ones right now, are based on adversarial learning. We're trying to reduce how much information predictions are revealing about some protected features such as race, while increasing or optimizing fairness and accuracy. But I'd like to illustrate this type of approaches with a very simple method that we actually described in the paper 2 years ago, which uses simple mathematics like linear algebra to improve fairness. So this approach actually, given some tabular data, you have some outcome, and you have a variety of features. So one of these features, or maybe even more of these features, are your protected features. This is the sensitive attributes, for example, race or gender, that you want your predictions not to discriminate against these groups, either gender groups or race groups or so forth. So you can think of this data as being being points. Each instance is a point in some high dimensional space. Describe it as variables. One of these variables features is this protected feature. Suppose one of these is race. Then we can make predictions more fair if we eliminate correlation between predictions and this variable. How do we eliminate? How do we eliminate? Well, we eliminate predictions by making basically predictions independent, which means we have to reduce correlation. So one way to do this is actually to figure out what is the space that's orthogonal to the protected feature. So you can use simple methods like Gram-Schmidt orthogonalization or a singular value decomposition to find the space that's orthogonal to the protected feature. Basically, it's linearly independent with the protected features. And you take all other features and you project them into the space. So these projected features are going to be, by the construction, they're going to be independent or uncorrelated with the protected features. And then you can use these features as variables in the models. Actually, here's another little additional feature we can add. So we can actually use parameter lambda to control, we can construct new features which actually mix between the original vector and the projected vector, and using parameter lambda to control how much the new vector we're using to explain the data, how much it actually aligns with the original vector or with projected vector. Okay, so this is the projection approach, and this has a number of benefits, meaning that this new fair or debiased features that are projected into the space, they're still retain the meaning of the original features. So the models you will learn with this are still interpretable, but then you can use this new fair or debiased features within any of your favorite prediction models, such as regression, decision trees. You can even use them with neural networks. And as I'll show you, they actually lead to better predictions that are more accurate and more fair. So here's one way, actually. This is we're evaluating these different algorithms, including our algorithm, which is fair logistic. And all the fair ones are this different models using this debiased or fair features. And this is the state of the art, some other methods are described. And here I'm evaluating, showing results on COMPAS, the same COMPAS data. And this is illustrating also the fairness accuracy trade-off. So here, fairness is measured by the correlation between predictions and the protected features. So how much does predictions, this is risk score prediction, so I'm creating a model of risk, how much are the risk scores revealing information about race? So this is the correlation one. So 0, it means it's completely fair. This predictions are not revealing any information about race. Versus accuracy. So how accurately is the model, the predicted risk scores, how accurately do they actually predict reoffense or not? So overall, you see this kind of this relationship, which is fairness accuracy trade-off. As you make the model more fair, push it down, you reduce accuracy. So if you make it more fair by reducing correlation between protected feature and outcome, you necessarily reduce accuracy and vice versa. But different models actually handle this trade-off differently. And our models, which are all these points here, these are the models using these fair features, they can actually give you higher accuracy at the same amount of correlation, or if you fixed some level of accuracy, they can actually reduce the correlation, but basically make it more fair for a given value of fairness, accuracy. So this is how the models improve on that fairness accuracy trade-off. And they also improve on the balance calibration trade-off as well. So balance here is measured by the difference between the mean risk scores in the two classes, blacks and whites. So lower is better. And calibration error is the difference between the area of the two curves, calibration curves. So lower is better as well. And you see overall, there's this relationship with this trade-off. You can't reduce, when you reduce one, you necessarily increase the other. So reducing the calibration error increases the balance error. And if you reduce balance, you necessarily increase calibration. This is the inherent, the trade-offs, incompatibility between balance and calibration conditions. But our models, which is shown here, these groups for the negative class and for the positive class, actually achieve better balance at the same calibration and than state of the art and vice versa. So this shows that you can actually get more fair and more accurate models, more fair models and better calibration while maintaining accuracy, high levels of accuracy as well. So you can actually improve through the model by getting better representation of features. Okay, so this was basically, well, I mean, I have a lot more to say in the topic, but this was kind of driven as illustration of the main points within these three different ways that biases in data can affect prediction, explanation, and fairness. And I showed also how we can control for some of these biases by identifying the confounders that represent different groups, heterogeneous groups that might have different results, and some of the methods that we can debias the data to identify, and by identifying these hidden groups. And of course, I want to thank all my collaborators who have contributed to these efforts over the years. And I would welcome any questions you have.
Thank you so much, Kristina. So time for some questions. I have one actually, sort of the trade-off question is actually it's a very important one. So many of the factors, right, the relation between data and the factors, right, like in your illustration, the protected factors or things that we talked about are typically for fairness, like race or some personal attributes or some sensitive factors. the information contained in the data about these factors are quite varied, right? And naturally, sort of. So when we try to sort of create methodologies to mitigate sort of the fairness effect, right? It creates some way, and the relation between sort of other factors. You're always going to have some amount of accuracy fall, and one that is dependent on the kind of construct or sort of the interrelation between these protected variables, right? Because we know that, say, even within, again, say you have the data and we have factors like, say, age, say, gender, or as seen through this lens of this data. And there's a relation between those constructs and through the data. And how we mitigate them is like quite varied. So are there sort of, more information theoretic type analyses that are methodologies that people are providing guidance to see, okay, here's this operating point or where we want to be. This is how much we can guarantee or expect in terms of, and there's always going to be, a cost associated with achieving something else.
Mm-hmm.
Yeah. So
well,
what are your thoughts on that? Yeah.
You're talking about kind of auditing data, trying to audit data to see the sources of bias and how much bias. No, we lost. Wait, I don't hear you. Wait, was I the only one who lost the audio feed?
No, I can't hear Sri as well.
I can hear it as well.
Huh? You don't look like you're muted, but we had some video glitch and then we lost this. Oh, now you can see it. Okay, try it again. Still can't hear you. Maybe you should rejoin, but basically I wanted to clarify your question, because, I mean, I've seen there are efforts right now, as far as, like, if I understood you correctly, one of the ways that you can do it is like auditing data for hidden biases. So one of the efforts I've seen is kind of data set nutrition label, kind of a data sheet or something that describes the data, how it was collected, for what purpose, which, the purpose and the methods for which the data was collected might also hide or contribute great biases in them. I can hear it typing, but maybe not sure it's typing. Oh, now I can hear you. Good.
Can you, yeah.
Yeah.
Yeah, thank you for that, Christina. So the point I was trying to make, like, in practice, that different factors have sort of different interrelation between these factors and with the data, and so sort of mitigating for them may have varying sort of limits, like, the fairness accuracy trade-off curves that one would provide. So.
But I didn't actually had slides, but I didn't talk about, for example, Bergson's paradox is one of them.
Yeah.
It sounds like you're familiar with Bergson's paradox, but maybe others are not. And it's basically, you can have just the mere act of observation induces a correlation between features when there is not to start with. So the kind of canonical example is like, why there are no nice, attractive guys. And I apologize for the cisgender implications of everything, but you could think, why are there no, but this is the example that's described in Wikipedia. So you can think about, there's a bunch of guys who are available for dating by women. And if you plot attractiveness versus niceness, there won't be any relationship.
Yeah.
People are just, there's nice people and not nice, and like no relation whatsoever. But the fact that people choose, for example, to date people who have certain characteristics of niceness and attractiveness from both sides. Women choose guys, so there's that creates some exclusion zone for them, but guys also choose women, which creates another exclusion zone. Together, these exclusion zones exclude some data, so the only people who are dating actually are like highly correlated, between niceness and attractiveness. So even though there's nothing, so you can think of dating as a way of measuring, observing the data. So the mere act of measuring induces a correlation when none exists whatsoever before. So data is really, really tricky. And a lot of what data tells us is actually already constrained by how the data was collected.
Yeah.
Yeah. So it's a really tricky thing to be working with real data, to be learning about human behavior from the data.
Other questions, comments?
Yeah, there's a
professor. Yeah. Oh, sorry. Please go ahead with the question.
Oh, there was Edward here said, how can we find the bias or just the bias by using some models? Should be okay. How do we find? It's the same question. How do we find bias? Basically, you should assume that whenever you get the data, you should assume that it's somehow biased already. So the question is, how do you find what biases are operational? So I think we just, well, I don't have a good answer to that, except saying like you should have the kind of, there should be, there's some standard statistical tests you do whenever you build models. There should be a similar set of standard statistical tests you do to identify, to audit the data for biases. You can start by identifying Simpson's paradoxes, the way I was describing before, like some measures on the variables that you did observe, start disaggregating data based on those variables to see if you can get different trends there. But that's just the first step. There's many other, because you might not have observed all the relevant features, or there might be other time. So information theoretic methods and statistical methods do not yet exist kind of to stand and deal with this, but we are developing them right now.
Raghu?
Professor, thank you so much for the talk. I have a question, I think, on similar lines that Shri was asking. So the null projection approach that you just showed, right? So there's an inherent assumption that the target task that you have is unrelated to the protected variables, right? For example, in this case, the compass does the task of predicting recidivism. So that is unrelated to the gender or the race of the users, right? But in some cases, there could be scenarios where the target task could be related to these factors. For example, say face recognition or speaker recognition. In those cases, the gender is an attribute, is an identity attribute, which can help with the task itself. But then you do not want the face recognition algorithm to be biased depending on the gender or the race, right? So how do you have any thoughts on how you can mitigate bias in those scenarios where just projecting it on the null space will not suffice, because that's going to degrade the utility or the accuracy, right?
Right. Yeah, and the same thing actually arises in medical scenarios as well, where race could actually, for some diseases, it's actually you need to take race into account. You can't make the outcomes completely independent of race.
Yes.
Or gender, of course. Obviously, men and women have different health conditions. But so I think you need to redefine your measure of fairness then, because again, you don't want to misclassify people based on their race. So I think you maybe pay more attention to the balance condition, and maybe that you can make predictions more fair to the balance condition. And I would say that necessarily, though, you might reduce the accuracy if you wanted to reduce the disproportion of the mistakes. That might necessarily reduce accuracy.
Yeah.
Orthogonalization might not work, but again, also the orthogonalization method I described before, it also only works. It only makes takes out the linear correlation between them. So there could be some nonlinear dependencies, which some method will be able to exploit to get better predictions while taking out the linear correlation. So, but in general, yes, it is a. And I think you'd have to define your fairness metric in a different way.
In fact, that's very true. It's also the same sort of trade-off between protecting the protected variables, right, which may contribute to the sort of the inference, which may in turn also be needed for some personalization, right? Like in some cases that knowing the age, like it's a child, may dictate, how you provide particular sort of treatment or than when it's not, right? You might want to have additional security measures, right? But knowing that itself is like, so there's this inherent sort of trade-offs or conflicts that are involved, and knowing what choices one makes, right, becomes important. But providing the tools like these analysis sort of is essential, that we'll have the ability if we want to.
And it's become so tricky once you have also some legal constraints that say that you're not supposed to use some of the legally protected features like race, gender, age. They're also legal, and you don't want to use those in decisions, in high stakes decisions. That I don't have the answer to that. It's a really tricky problem.
Yeah, it's a complex optimization space, and even though we might have sort of arguably information that'll support the inference, better accuracy and so on, we may constrain the problem such that maybe you can't use it because of say legal constraint or ethical constraint or so on. So knowing those bounds of where we can operate is like is important, and I think these methodologies and tools help us shine light on this, that these possibilities, instead of just throw everything in the kitchen sink, or let me just focus on just one aspect of accuracy. And that's one of the lessons I think important takeaways for me.
Right. And I should have started actually this talk with a motivating example from our tiles example, where we're trying to predict cognitive score, like cognitive ability from sensors data, and we found that people who move a lot have higher cognitive ability. And then it was just like kind of Simpson's paradox, because people who move a lot are nurses with more education, and people who did not move a lot were like lab techs that had less education. So it was actually just picking out nurses versus lab techs rather than saying that movement was correlated.
Yeah, in that user group. Yeah, exactly.
Yeah, that's right. In that particular user group. So the way we were measuring, but like the relationship, we were so happy. It's like, we can predict cognitive ability from sensor, from Fitbit, and then turned out to be all totally confounded by the job type. So look for confounders in your data as a first step into understanding the biases.
Any final questions from any of the remaining people? Well, Krishna, thank you so much. I know for taking time. I know this is
no, my pleasure.
Traveling. We really appreciate it, and we'll make this talk available in part of the series. Very, very, sort of right on target for this group to think about.
And there's still many more problems left that haven't been solved. So this is a really rich area for further analysis, especially dealing with some of the questions we do ask.
Thank you so much, and thanks to everyone.
Right. Thank you all. Thanks a lot. Bye-bye.